class, Adam Ward here. This is our second of two videos about weirs, and we're going to focus in this one on broad-crested weirs, having previously discussed sharp-crested weirs. So what's a broad-crested weir? It's a weir that is more than one instance in the flow. These broad-crested weirs have length in the direction of flow. And so pictured on the left-hand side, you can see a broad-crested weir in an irrigation canal. So that's a trapezoidal canal, and what you see in that sort of bright white color is that there's basically a ramp up, then a flat surface, and then a much steeper ramp down on the right-hand side. And in the bottom left, you can see what that looks like when water is running over the top of it. On the right-hand side are two flume experiments that have broad-crested weirs in them, just so you can get a sense of what the profile of the water is looking like as it goes over top of one of these. What I want you to notice here is that the way a broad-crested weir functions and the reason that we use these, we put this in the way, and then rather than creating a free jet over the weir like we did with a sharp-crested, the purpose here is to accelerate the flow to hit its critical point while it's over top of that broad-crested weir. And so you can see I've labeled in the top right YC. We reach that critical depth as we get to the end of a broad-crested weir. So in a schematic perspective, it might look something like this. And you'll notice, again, I'm emphasizing as you go over top of the weir, you achieve a Froude number equal to 1. Before the water exits or before it passes by. And that Froude number of 1 means that we're at a critical depth and the associated velocity. So Froude number of 1 over top of this weir is the critical piece. You'll notice that over on the left-hand side, things look very similar. We have an incoming velocity, a depth of y1, and we're describing this weir based on its height, pw, its length in the direction of flow, capital LW in this case, and again that capital H, right? What we want to be able to measure is that depth of water upstream of the weir that's flowing over it. And we're going to measure that and use that knowledge to be able to calculate what is the discharge. Okay, so from that schematic then, let's work through the first question. Well, what is that critical depth? And so we can write the energy equation from point 1 to point 2. So I'm doing that here. And you'll notice that I've described in these terms that I'm underscoring in blue, those would have been Z1 and Z2 in the most generic version of our energy equation or Bernoulli equation. Notice also that we're not accounting for any head loss. Again, there is likely to be head loss in a real system, so that's one assumption that we're making. Now, from our energy equation, we can pick points that are both at the free surface, so P1 and P2 equal to 0. And there's a PW, height of weir, on both sides. We can get rid of that term. And again, noted in blue, what would have normally been Y2 and V2, I've gone ahead and put those in as the critical depth, YC, and the critical velocity, VC. Okay. So what we have left from there is capital H minus critical depth, YC, or the change in elevation from the head above the weir over at point 1 to the head above the weir, or the depth above the weir at its ending point. So H minus YC equal to the change in velocity head, Vc squared minus V1 squared over 2G. Now, a couple of things that we'll assume away, as we've done before. Let's approximate the upstream velocity as 0. Again, that's not strictly true, but if it were 0, we could drop that term out. And the other critical piece of knowledge is to remind ourselves that as we hit the end of that broad-crested weir, we're at critical flow, Froude number equal to 1. Now, in order for Froude number to be equal to 1, we know the numerator and denominator in the Froude number must have been the same, or in other words, that critical velocity, Vc, is equal to the square root of gravity times the critical depth, yc. So with that assumption in purple, and that substitution based on the Froude number, we end up with a depth of flow over the weir, or a critical depth, YC, of 2/3 of the height measured upstream of the weir. So 2 times capital H over 3. Now, this is great. This relates the two depths to one another, but it doesn't yet get us to discharge. So on the next slide, let's get to Q. Now we know Q could be estimated as area multiplied by velocity. And we'll derive this for a rectangular system where we've got vertical walls, so a cross-sectional area of B wide multiplied by YC in depth. Well, it makes our substitution. Discharge is equal to width times depth, B times YC, multiplied by that critical velocity, VC. And again, because we know the Froude number is equal to 1, YCs and VCs become substitutable using this equation. And so we can calculate here, discharge is equal to the width B times the square root of gravity multiplied by YC to the 3/2 power. Now a couple wrinkles here. If instead you know the upstream values, and that's what we're much more typically measuring. If you know the upstream values, specifically meaning if you know H. So if you're measuring capital H, not measuring YC, that's what we tend to measure. You can use the equation that I've written out here. Discharge is equal to a coefficient for weirs, B for broad-crested. So CWB is the broad-crested weir coefficient, multiplied by width of the weir B times root G times 2/3 raised to the 3/2 power times that depth H raised to the 3/2 power. And once again, you get an empirical equation for that coefficient. Now, what I want to point out to you here again is we've gone through the exact same steps that we did on a previous slide, on the sharp-crested weirs, excuse me. We took our problem, we made a few assumptions to simplify it, we did our derivation, we further simplified the problem, and then we didn't love those simplifications, so we're putting this weir coefficient back in as essentially a correcting value. What I do want you to also notice is the set of equations that I wrote for you here are based on a rectangular channel. And so we looked in the beginning at some Flume experiments where that would be the case, and we also looked at some triangular or trapezoidal channels where that may not be the case. And so again, I'm showing you one derivation to help you get your head around how and why this works, but you'll want to go through this process to lock in those derivations and get them correct for any situation. Okay. One last item is just thinking about how this actually functions and what the assumptions are that we're making. So on the left-hand side, when we have a ratio of height of water over the weir, capital H, to length of weir, LW, of less than or equal to 0.08, this makes me a happy man. In other words, this weir is much, much longer in the direction of flow than the upstream depth over the weir. Now, in this case, you get perfectly horizontal streamlines. The viscous effects are sufficient that you actually get to that critical flow condition. Right? So that's what we would ideally achieve. On the other hand, on the right-hand side of the screen, with our sad face, if you design a weir that is too short, so if it's not long enough in the direction of flow, or if it's got too much depth of water upstream, you don't meet those assumptions. You may not get to critical flow over top of that weir, and it may actually start to behave more like something that's halfway in between a sharp-crested weir from our last video and the broad-crested weirs that we've gone through here. So again, when you're designing a weir, you control the geometry, and you want to think about what is the maximum discharge that I want to measure, what is the depth of water that's going to generate, how can I estimate that value using what I know about open channel hydraulics, this broad-crested weir being in the middle, This looks something like the problem that we did a few lectures ago, where we had a channel with a step, an upward step in the bottom. And so you can actually go through and design these broad crested weirs to make sure that they're going to function for you across the range of discharges that you expect. All right, folks, that's what I wanted to say about broad crested weirs. Again, this takes advantage of the energy equation as its basis. In the case of broad crested weirs, you're also taking advantage that you understand critical depth and Froude numbers to get to the design. All right, folks, that's what I had for you. Thank you very much.